Phil Halper, welcome to the podcast.
Thanks, Miles. Great to be on.
So, the title of your forthcoming book is Battle of the Big Bang, The New Tales of Our Cosmic Origins. What is the Battle of the Big Bang? What are you referring to?
Well, I think in the simplest form, we could say the battle is to correctly describe what happened 13.8 billion years ago. So that's one form of the battle, but there's other sort of sub battles. For example, there's a popular idea called inflation, and that is the consensus view, but not everyone agrees with it. So there's quite a fight going on amongst cosmologists as to whether that's valid or not. There's also battles about whether the universe is eternal or had a beginning, whether it's one of many or unique. So there's many sort of what's the right form of quantum gravity? There's lots of battles there, string theory or loop quantum gravity, or maybe another theory altogether. Do we even need quantum gravity? So there's lots of fights going on within physics at the moment, and they're quite tasty. Um, and that's what the book is about, documenting all these different battles. It really should be battles of the Big Bang.
Right. So, that sounds like multiple
Mm.
lines of fire and issues that arise within cosmology where there's controversy, I take it.
Yes, absolutely. Yeah.
You can see a fly going around me. There's no way I can
I
catch
can.
that. So, let's talk about some of those.
Great.
The issues surrounding inflationary theory.
Mhm.
I don't know how technical you'll be able to get or how technical we should get, but what is the controversy about inflation? Because it was my understanding that it's the dominant paradigm of cosmology as an adjustment to the standard model.
It is the dominant paradigm, but not everyone is happy with it. So maybe we should just lay out what inflation is, why cosmologists tend to accept it, and then why the skeptics are skeptical of it. Um, so, first off, inflation is the idea that the universe underwent under very rapid exponential expansion. So, how rapid? Numbers quoted as something like the doubling time. So, think of the doubling time of COVID, for example. If we'll think put ourselves back into the pandemic, I think at its height, it was doubling. The number of rates were doubling every 2 days. That was the fastest rate of growth. Um, and here we're talking about the universe doubling in size every 10 to the minus 37 seconds. So we're talking, what's that? 10 trillionth of a trillionth of a trillionth of a second. So that is a very fast doubling time. So now you might ask, why do we care how fast it grew? Um, what difference does that really make? Well, it has huge implications. So when it potentially solves a number of very puzzling aspects of our universe. So I won't go through all of the puzzles. You'll have to read the book to get all of them, but I'll just give you two, let's say. So one puzzle is that when we look at the cosmic microwave background, it looks extremely uniform. It's come to thermal equilibrium. So imagine you take a pizza that's been cooked out of the oven. It will cool down. It will equilibrate with the temperature in the room, but it takes some time to do so. It doesn't happen instantly. So you can calculate how much time there's been for this to happen, because all the CMB photons are roughly at the same temperature. And that takes time for that to happen. And there hasn't been enough time since the Big Bang for that to happen. So effectively, this is known as like breaking causality. This is an acausal process, unless something comes in to fix it. So that's called the horizon problem. Another problem is called the flatness problem. So the flatness problem is the one you often hear about in the fine-tuning context. So basically, the universe can have different geometries. So if you think of three shapes: one a flat piece of paper, another a ball, and the other a saddle. They all have different curvatures. So a flat piece of paper has no curvature. The saddle has negative curvature, and the ball has positive curvature, or a sphere. Now, what cosmologists of the 1970s knew was that the flatness of the universe was quite close to 1. But what a cosmologist called Bob Dickey pointed out was this was very unstable. So it's a bit like a pencil balancing on its end. Um, you'd have to balance it very, very carefully to let go of it and stay there. And any kind of disturbance should knock it over. So similarly, the idea was that the flatness of the universe was very unstable, that it really had to be incredibly finely tuned at the earliest moments for it to stay flat today. Any tiny deviation from flatness would knock it well away from flatness. So how is it that the universe is still flat today? So that was a very big puzzle. And what inflation does is it solves those puzzles. Um, so the horizon problem goes away because if you have very rapid expansion, then the early part of the universe can be much smaller. So they could have been in thermal equilibrium, and then inflation would stretch the universe out. So that solves the horizon problem. It also solves the flatness problem because inflation. Well, there's two ways to think of it. One is you can think of it as um, the equations used to demonstrate this fine tuning assumed that the universe had a positive gravitational attraction. In inflation, you actually have a kind of negative gravitational force or repulsive force, and that turns the equations upside down. So now, rather than being driven away from a flat solution, they're driven towards a flat solution. But you can think of it another way, which is just imagine standing like I don't know if have you ever seen like circus shows where people stand on like gym balls? Quite a difficult feat, right? I couldn't do that. That must take some practice. Now imagine you were standing on one of those gym balls and you just grew the size of the gym ball to it's the size of a planet. Pretty easy to stand up on that because in fact that's what we do, right? And so what happens is the flatness disappears. Um, it becomes sort of taken away from your view by the enormous change in scale. So inflation solves a lot of these problems, and I've only mentioned two. There are more. Um, so that's why people take inflation very seriously, and it also seemed to make predictions that were confirmed by observations. So even better. So everyone's very impressed with inflation, or most people are. Now, where it becomes really interesting, why do we care? So what if the universe had a really rapid period of expansion? I say there's two reasons why we really care. One is that if inflation happened, it must have happened before the Big Bang, not afterwards. So when a lot of textbooks say inflation happened just after the Big Bang, but that does not make sense because the reason is that when we think of the Big Bang, we think of an evolution from a hot, dense state. That's really what we should think of when we think about what the Big Bang means. But in inflation, the universe is cooled down to practically zero temperature. Then, at the end of inflation, it heats the universe back up. Um, so we can really think of then, if the Big Bang is understood as the evolution from this hot, dense state, then inflation is actually a pre-Big Bang scenario. That means there was something before the Big Bang. Even more importantly, inflation is thought to lead to what's called eternal inflation. That means that when you get this sea of inflating space decaying and it creates like what we call a bubble universe. So our universe would be one bubble in a sea of inflating space, and there would be infinitely many other bubbles. So this is thought to create a multiverse. And that's very interesting from a philosophy of religion perspective, because when we come to the Kalam argument, what we often hear is that the Big Bang defeated the steady state, that the steady state was ruled out. Now, what was a steady state? This was an idea in cosmology where it was thought that the universe was basically unchanging over time. They constructed this model such that basically you get this expanding universe, but in the expanding space, new matter is being created, galaxies sort of popping out of the vacuum. And over time, it would all look the same. So it has no beginning and it has no end. Now, that was ruled out by observation. But this creation of matter was driven by a hypothetical field called the creation field. And we know from observations that this model is wrong. But if we think about eternal inflation, then we can just replace the creation field that was used in steady state with this, what's called an inflaton field, the field that drives inflation. And we can think of, instead of galaxies sort of being continually replenished, that's what happened in the steady state model, it's bubble universes. So if we just change the scale, we find that inflation just kind of is the steady state model, but at a very different scale. So this narrative that you hear, the steady state has been defeated, in a way is wrong, because inflation kind of rescued the Big Bang. And as you said, it is kind of a consensus view. But it did so by, in a way, resurrecting the steady state in the form of this inflating multiverse. And that seems to be the dominant view of how inflation acts and what is the result. So we get these very profound implications. One, that inflation, the Big Bang is not the beginning. Two, our universe is not alone. And three, maybe we kind of revive the steady state in some sense. There are a lot more things to say and unpack about that, but maybe I'll pause there if you have any questions, and then we can come to the critics.
Yeah, so I'm so tempted to jump right into the issues it raises for the Kalam
Yeah,
cosmological argument, but
right.
before we get to that, I'll table that
Yeah.
for the time being. I'd like to
Okay.
hear what you have to say about the scientific critics of inflation. I
Okay.
imagine
Yeah.
their criticisms are not, well, this refutes the Kalam argument. We can't have that. So, what are the scientific criticisms of
No,
it?
they are not that. If you ask cosmologists about the Kalam argument, with high probability, they've probably never heard of it. They don't really care about that sort of thing. Some have, not all. Some have.
Some
Uh,
have, some have.
I mean, some of them have, because I've measured it because I made them appear in a film about it. I made a film, and I sent it to them, and and a lot of them were not familiar with it, and they were like, "Oh, this is really interesting." Um, but no, so the criticisms, there are different criticisms. So one criticism is that there are different versions of inflation. So the way we think about it is, in inflation, the universe is undergoing this exponential expansion. And so it's in this state which we call a false vacuum. So what that means in plain language is, you think of empty space, you might think of it as just being purely empty, sort of total nothingness. But in quantum physics, it's not that. It has energy. Empty space has energy. So the question is, how much energy? Now, when it's at its lowest energy state, that's called the true vacuum. But it can be trapped in what's called a false vacuum, where it has a sort of local low, but not a global low. So the analogy that's often given is, imagine a Mexican hat. So the Mexican hat has a sort of depression at the top and then a wide rim around. So the wide rim at the bottom of the hat is the true vacuum, if you like. And now imagine a marble that's sitting in a depression in the top. It can't get out. It's in this false vacuum. It's in a local minimum, but not a global minimum. And so, in order for inflation to end, because obviously the universe is not inflating right now, or not anything like doubling every 10 to the minus 37 seconds. So inflation has to end. And in order to end, it has to move from the false vacuum to the true vacuum. And it can do so actually through different routes, if you like. So that leads to different inflationary models. Also, they assume that there's this hypothetical field called the inflaton field that drives inflation. And there could be different types of fields, or maybe more than one field. So there's a plethora of inflationary models. There's an encyclopedia that it lists, I can't remember exactly how many, but it's somewhere between 1 and 200 different inflationary models. And to some scientists, this undermines the notion that inflation is actually a predictive model, because you could probably find one inflationary model that fits the data, and if that one doesn't work, you can find another one. So
Right, no matter
that's
your observations, if there's a model that corresponds to it, well, then your overarching theory probably isn't falsifiable.
Yeah, yeah. So that's one criticism. Another bugbear that people have is that it leads to a multiverse, and a lot of physicists love the multiverse, and a lot of them hate it. So those that hate it are against inflation. Now, there are a few people that would suggest, oh, maybe inflation doesn't lead to a multiverse. Maybe that's a mistake. So there's another route that people take, but it's not. I think the majority view is that inflation does lead to a multiverse. So if you don't like the multiverse, probably you don't like inflation. Another criticism is that the field that drives inflation is very hypothetical, and we don't have an underlying theory of physics that should predict the existence of this field. People would hope that it should be realized in the quantum gravity theory, like string theory or some other competitor. And some of them do hint that there is inflation, but it's not so straightforward. It's certainly, and there are alternatives to inflation that may be more direct results of quantum gravity proposals. So that's some of the criticisms. There are others. I mean, we could go on for a while, but I think those would be the main ones.
Good. That's very succinct and
Yeah.
helpful. There are those three critiques of the inflationary paradigm.
Yeah.
So that is one facet of the battle of the Big Bang is
Yeah.
inflationary theory.
Yes.
The second one, if I recall, is the question of whether or not the universe had a beginning. It's an adjacent issue. It's related, obviously.
Yeah.
So what is that area of controversy? Because I know enough about cosmology to know that it is not a consensus opinion among cosmologists that the universe had a beginning. But
correct.
I also know that many cosmologists do think that it did. I've spoken to a few of them, and they've indicated at least that much. So I know that's the case. It's not a consensus, which some people imply, but some people think, some cosmologists think that it is more likely than not. So beyond that, though, what is this controversy?
Well, first of all, when you speak to cosmologists, it may depend on which cosmologists you speak to, obviously. Now, one needs to be careful because not every cosmologist works in this area. In fact, my guess is that most cosmologists don't work in this area. You might think, surely you're a cosmologist, the Big Bang is your area of expertise. But actually, no. Most cosmologists probably work on things like the large scale structure of the universe, late time evolution of the universe, things like that. The number of cosmologists that actually work in early universe cosmology, what's called the very early universe, is probably a small subset of cosmologists. So it's always interesting to know when you're talking to someone who is an expert, be careful. Are they actually an expert in this area? Now, so there are models that have a beginning. There are other models that don't have a beginning, and others where it may be ambiguous as to whether there's a beginning or not. Now, what happened was in the history of this subject, it basically sort of runs like this. So people knew that there were these things called singularities in cosmology. They knew this going back to the 1920s with the work of Friedman and Lemaitre. And these are solutions to Einstein's equations where the space-time curvature, the temperature, the pressure, the density, they all go to infinity. And it's also a place where sort of trajectories of light rays sort of come to an end. They just stop. So this can be interpreted as the beginning of time. Now, what happened was these were proposed, but they weren't taken very seriously. In the 1930s, have you seen the movie Oppenheimer? So do you remember just before the outbreak of World War II, they published a paper about black holes, and in the movie they showed that black holes are kind of real, and Oppenheimer had proved this with his student Snyder. Well, what was interesting was that they had kind of proven that there were singularities in black holes, but their proof relied on a very simplifying assumption that the collapsing star was perfectly symmetrical. Now, you can probably guess that that is not very realistic. It's a bit like the old joke with the physicists. Let's see if I can remember the joke. I think it's a farmer has a problem with the cows not producing milk, and he asks a physicist to try and come up with a solution. And then 2 weeks later, it says, "Yep, I've got the solution, but it only works for perfectly spherical cows in a vacuum." You know, And that's what often happens in physics. You make these simplifying assumptions and then you get your conclusions. But the question is, are the conclusions generic or are they a feature of these simplifying assumptions? So the question about and in fact, physicists complain that the Oppenheimer-Snyder collapse was relying on these very, very simple assumptions that were almost certainly unrealistic. Then in the 1960s, along comes Roger Penrose, and he uses a different methodology, and he shows a singularity is still there inside the black hole, even if you relax those simplifying assumptions. So that was seen to be really robust. And then Hawking comes along and takes his black hole singularity theorem and adapts it to cosmology. And he says, look, if the future of collapsing matter is a singularity, then the past of expanding matter is also a singularity. So basically, he can try and take Penrose's proof and apply it to the universe as a whole. And that was seen as much more robust. So then the conclusion was, okay, the universe had a beginning and it had a beginning with a singularity. But there's a lot of assumptions in the singularity theorems, even the Penrose-Hawking ones. They are not vulnerable to this worry about perfect symmetry, but they are vulnerable to other. Exactly, yeah. But they have other assumptions that you can question. And the one that people mostly focus in on is that you're assuming Einstein's gravity all the way into extremely high energy densities, where quantum effects are thought to be pretty much inevitable. So then the question is, well, why should we trust this conclusion? But Hawking made a big deal that it would prove in the beginning of the universe. And I made a movie with Hawking, and the way he phrased it was, these theorems prove that the universe had a beginning, but they don't show how the universe began. But a lot of other people say, no, it don't prove the universe had a beginning at all. You can't trust this conclusion. Now, what happened in the early 80s? Well, Hawking took seriously the idea that we need a quantum update to the Big Bang. He came up with a model which is known either as the Hartle-Hawking model, because he worked with a guy called Jim Hartle, or it's also known as the no boundary proposal. So same thing, just different names. And his idea was that when you went back to the Big Bang, you can think of our universe as having normally 3 space dimensions and 1 time dimension. But actually, we lose the time dimension and we have 4 space dimensions. So the universe transforms, if you like, to being in some sort of timeless state. Now, there's a question of interpretation here. Does this model have a beginning or not? Because on the one hand, time does not go infinitely far into the past. But on the other hand, you could say there's no point that you can mark on the beginning, because it's like a shuttlecock. It's not, rather than with a singularity, there was like a point of infinite density. You don't have that in the no boundary proposal. Another ambiguity is that it also introduces a notion of what's called imaginary time. So people that know mathematics might have heard of imaginary numbers, but maybe I should explain to those that haven't heard of them. So if you
Sure.
think of the number 9, right? What's the square root of 9?
3.
And
-3.
yay. Okay. Right. A lot of people don't get that. Right. So, but there isn't any conventional number that will. So -3 times -3 is +9. +3 times +3 times +3 is also +9. Now, there's no conventional number that you can square to give you -9, right? Or any negative number. But mathematicians invented this kind of funky numbers, which we call imaginary numbers, that do square to negative values. And these are called imaginary numbers, and they're used in quantum mechanics all the time. So now what Hawking did was he said, well, kind of we can introduce imaginary time into the origins of the universe. And now you could actually follow the universe back in real time and in imaginary time. Do you get the same answer? And some allege that what you get in the Hartle-Hawking model is a beginning in imaginary time, but not one in real time. There's a debate as to whether it really has a beginning in real time or not. So there's an ambiguity there about whether this model has a beginning. But nevertheless, Hawking definitely did interpret it as having a beginning. So a lot of so he kind of gave a talk saying, well, so his view, I think, was that we still have this beginning. We don't what his quantum cosmology did was just to explain the beginning in scientific. The science doesn't break down everywhere in the whole structure of space-time. You can describe it using physics, whereas in the old singularity theorem, the physics just broke down, because when you get infinities in the equations, you get what's called a loss of predictivity. So that's you just don't get a sensible answer out of your equations. So it's a bit like dividing by zero. Do that on your calculator, you just get undefined. So now you do have that. So he was satisfied. Well, we still have a beginning, but some people interpret that model as not having a beginning. But there was another model from Alex Vilenkin, a sort of rival to the Harter-Hawking model. This is called the tunneling from nothing model. And that was another attempt at doing sort of quantum cosmology. And there, I think it's less ambiguous whether there's a beginning. It's pretty clear there's a beginning in the Vilenkin tunneling from nothing model. And these were the models that people were exploring, and they were kind of the dominant. When people talked about quantum cosmology, they generally were talking about these two models. But what's happened in the last 2 decades, roughly, maybe a bit more than 2 decades, is that people have taken ideas from string theory, from loop quantum gravity, from other theories of quantum gravity like asymptotic safety, causal set theory. I'm going to drop a bunch of names, but the point is there are these other theories which are really more fundamental theories, because these are the two ideas that we mentioned before, the Vilenkin tunneling from nothing model and the Harter-Hawking model. These are called quantum cosmologies because they use notions from quantum mechanics and they try and stick them with relativity. But what they don't do is take a quantum theory of gravity and try and go from the bottom up and say, well, develop this theory of quantum gravity. Now tell me what happens at the Big Bang using it. That is the program other people have tried to do. That wasn't what Hartle and Hawking were doing, and that wasn't what Vilenkin was doing. And what they find in many cases, not necessarily all, but in many cases, is that the Big Bang was not the beginning of the universe at all. A lot of models have what's called a bouncing universe. So the universe was collapsing before it was expanding. So in these models, there is no beginning. Now, so that's one way in which the battle is being fought. Are these models valid? Are they interesting? Are they right? Could we see them implementing some of these ideas like Hartle and Hawking had, or Vilenkin had? So that's one way in which people are challenging the beginning. Another way to challenge it is to challenge inflation and say, well, look, if we don't believe in inflation, let's go back to those critics of inflation. Well, I think the way that science works, see, a lot of people think the way that science works is falsification. You have a theory, you try and falsify it. If you don't falsify it, it gets up and up and up in your esteem every time you fail to falsify it, but you could. But I don't think that's how science works. In my opinion, it's much more of a competitive process. You get a theory, it does well. You're not going to usurp that theory unless you've got a better one, or unless you show some really fatal flaw in it. So really, the critics of inflation have to do better than inflation. They have to come up with alternatives and say, right, how do you solve the horizon problem? How do you solve the flatness problem? And probably the one problem I didn't mention, most important of all, is how do you get structures to form in the universe at all? Because if you started off with something very uniform, you wouldn't get any structures. So how do you get them at all? And inflation can explain that. So the alternatives have to do the same thing. And again, many of the alternatives are cyclic universes. And again, so they don't necessarily have a beginning. And so the beginning is being challenged, I would say, on two fronts. One is the quantum cosmology side. In the early quantum cosmologies, it seemed like the universe still had a beginning. That's why someone like William Lane Craig says, the beginning is still there, whether you have quantum cosmology or not. But I think he's just out of date, because the more modern versions of quantum cosmology don't necessarily have a beginning. And then you've got the people who maybe put quantum cosmology to one side, like Penrose, Paul Steinhardt, Anna Eas. These are people that say, look, let's not worry about quantum gravity because we don't understand that. We can do cosmology without quantum gravity, actually, and they think, well, there could be cyclic universes that can alleviate the problems of inflation, and so that's a second challenge, if you like, to the beginning of the universe.
Fascinating stuff. I think you've clearly mastered the relevant concepts because that was a very lucid explanation. So
Thank you.
there are various directions we could go in here.
Yeah.
And you beat me to the punch by mentioning William Lane Craig, because I was going to say, perhaps you've heard of William Lane Craig, and then launch into. William Lane Craig has argued for many years that the empirical evidence is pretty clear that the universe had a beginning, and therefore God likely exists, because if the universe had a beginning, there needs to be a cause for it. And then he will contend, you can argue, that we can derive many divine attributes by just analyzing what a cause of the universe would have to be like.
Mm-hmm.
So you have had a podcast appearance on the Majesty of Reason YouTube channel, and you've discussed
two podcast appearances.
Yes. So you've discussed some of Craig's alleged misrepresentation of the relevant science. So I just want to dig into that a little bit, and there'll be some overlap, some repetition from your appearance there, but we'll break new ground. So,
and I also going to do a shameless plug that we've made 2 videos on the Kalam argument. The first one was a sort of hour-long documentary with many leading experts, and then Bill Craig did a 4-part reply, and then we did another, I think, 70-minute reply with many of the same experts.
Yes, and I will also shamelessly plug that as well. They are documentary level videos, and he interviews the top leading experts, philosophy and cosmology. I don't know how you got into contact with them, and so after this, I want to talk to you about that, because we're in similar avenues here.
It's all Jedi mind tricks, basically.
Yeah, it's like, how did he get them? So they're very good. I recommend them highly.
Thank you.
So Craig has responded, as you know, to your interview with the Majesty of Reason, and he has said the following, quote, "You can avoid the singularity by denying that one condition of the BGV theorem," which we'll talk about, "but Sinclair and Vilenkin emphasized that the resultant models are faced with a plethora of problems that preclude those models being physically reasonable. So we can be relatively sure that the correct model will belong to that class of models that obeys the Borde-Guth-Vilenkin theorem and features a beginning and a finite past." So to expand on that a bit, the Borde-Guth-Vilenkin theorem is an established piece of cosmology. Its implications aren't as clear. But what the theorem shows is that any model of the universe that entails that the universe has been, on average, in a state of cosmic expansion throughout its history, a positive expansion, cannot be extrapolated to past infinity. It cannot be eternal in the past, roughly stated. And Craig's point is that this theorem excludes several different models at once that would have been thought to restore an eternal universe, like eternal inflation. Because this model represents the universe as inflating throughout its history, it actually can't be past eternal given this theorem. And so there's only a narrow set of models which could even possibly be past eternal, but those models are plagued by independent problems, and therefore we can draw a reasonable inference that whatever model turns out to be true is going to be one that features the universe as in a state of cosmic expansion throughout its history, and therefore has a beginning. What is wrong with that argument, Phil? Why? Why is that bad?
Okay. So first off, let's clear one thing up.
Okay.
I hope we can really straighten out. First off, I got it from Alan Guth. The pronunciation is border, not board.
Okay.
Okay.
I heard it.
Yeah.
I'll take it. I will always and forever now do that. And I heard it once pronounced that way, and I thought, maybe I should. So that's
yeah. So that's how Alan Guth pronounced it. So I'm going to guess that he knows how to pronounce his colleagues' names.
I would think so.
So, all right. So let's start with BGV. Okay. So how does this theorem work? Basically, there's so many problems. So where to start? Firstly, there are many ways actually you could get around the conclusion that there has a beginning. The most obvious one, the most clearly straightforward one, is that the universe wasn't always expanding, right? that seems a very easy way to get around the conclusion. Now, what Craig says is that universes that are contracting are unstable, and therefore they would not sort of bring out the smooth universe that we experience today. So that is, and Vilenkin has said that as well. Now that's problematic because whether the universe is stable or not depends on what assumptions you make about what matter fields are present. And you can make different assumptions and get different conclusions. So there was recently a simulation. So remember I said that some of the opponents of inflation are fans of a cyclic universe. So one particular group who are pushing the cyclic alternative is Paul Steinhardt and Anna Ias. Now, Paul is quite important in this story because he was actually one of the founding fathers of inflation. So when inflation was first developed by Alan Guth in 1979, when he first developed it, he almost immediately noticed there was a serious problem with it, and he did not know how to solve it. But because it could solve several problems at once, he said, "Look, this theory is really good, and but I don't know how to solve this particular problem. It's called the graceful exit problem. It's basically how is inflation supposed to end, and they couldn't get it to end basically." So Paul Steinhardt was one of the cosmologists who found a way to get it to end and solve what's called this graceful exit problem. So in fact, the Dirac Medal was awarded to 3 cosmologists for inflation. Dirac Medal is a very prestigious medal in physics, and sort of one shot down from the Nobel Prize, if you like. And it was awarded to Guth, Andre Linde, and Paul Steinhardt. So those were considered the 3 founders of inflation, although Guth came up with it kind of first. Actually, there were people even before Guth, but they didn't realize what inflation could do. So they're kind of not really given credit. And I think that's fair. Guth was the one that really realized what inflation could actually do, how it could solve all these problems. So I think it's fair that he gets the credit. But anyway, so Steinhardt's pushing the cyclic alternative. Now, in order to get a cyclic alternative to work, they assume like an extra field in the universe that basically changes over time. So it would replicate a cosmological constant, which is thought to cause the universe to accelerate in its expansion. So now this field has some interesting. You might say, well, adding an extra field, that's a bit dodgy, you know, not very parsimonious. But you know what? Inflation does the same. So if you're going to be worried about an extra field, some hypothetical field, well, you should kind of rule out inflation as well then. So they have a different field, and actually they've run simulations with like some of the leading gravitational, what are called oh, I've forgotten the name. There's people that basically work on computing the implications of the relativistic equations, and they're numerical relativists. That's the phrase I'm looking for. So numerical relativists, they're basically, yeah. Thank you. Yeah. So they work with numerical relativists, and they've shown that these things do create a smooth universe. And in fact, they can smooth the universe even better than inflation. In fact, they argue inflation doesn't smooth the universe as advertised. Now, I'm not going to say they're right. This is an area of active research, and someone publishes a paper and they make a claim like that. You have to treat it with a bit of a pinch of salt, because someone else might find a flaw, and there's a back and forth that goes on. And we're at the frontiers of knowledge here, so we should be very careful about not sort of taking any claim that one particular cosmologist makes and thinking that it's now fixed in stone. So these people have claimed that you can get a perfectly smooth universe out of a contracting universe. Another way to look at it is to go the other way and say, look, rather than try and go back and plug forward from a contracting universe to our expanding universe, why don't we just go backwards in time? We know the universe is expanded. Let's wind the clock backwards. We go back in time, we're going to see a denser and denser and denser universe. We'll get to a point where there's a singularity in classical physics. Let's, at that point, put some quantum corrections in and see what happens. And what they see happens in many models is that the universe stops contracting because we're running backwards in time, don't forget, and then it starts expanding again. So that shows you there was a contracting universe, if we trust those models. So it just seems wrong for him to rule out a past contracting universe. It just seems totally unjustified, in my opinion. This is a very active area of research. There are people that will, here's what Craig does, I think, is that, you've got a controversy in physics about these early universe models, because of course we do. We're at the edge of knowledge. So there's always, any scientific field where you're at the edge of knowledge, you're going to have controversies. So what Craig does is selectively find problems with the models that he doesn't like a contracting universe prior to expansion, and then ignores the fact that I could write a parody argument to any article that he has and say, well, look, here's all the problems with models with a beginning. Like in the Hartle-Hawking model, they have to assume this really weird sort of probabilistic framework, which they call it top-down and bottom-up probabilities. So, and I won't bore you with what they are. The bottom line is there are issues with any model, right, of the early universe. That's if there weren't, we probably wouldn't have a controversy. We'd have a settled-on model, right? But of course, we don't have a settled-upon model. So what he does is selectively find problems with the contracting universes and quotes the critics of contracting universes, and then just ignores the fact that there are replies and that we don't necessarily know the answer. Now, on top of that, there are other people that have criticized, even forget whether there was a contracting universe at all. Let's assume there wasn't. Other people have said, actually, there could be flaws in the BGV theorem. So the way they assume, how they calculate what the average expansion is, it's been alleged is flawed. Others have said, well, when we go to a more quantum mechanical description, we lose the conclusion. And in particular, so give you another example. One of the assumptions in the Borda-Guth-Verlink, it's not true that the only assumption is that the universe is expanding on average. That is just not correct. Another assumption is that you're using classical physics. So one alternative to inflation is, rather than change the expansion rate of the universe, you change the speed of light. Now, that will actually do the same thing as inflation, because remember that inflation, there wasn't enough time. Sorry, in this classical model of the Big Bang, there wasn't enough time for the universe to become in thermal equilibrium. Now, what inflation does is it makes the original part of the universe much, much smaller. So it was easier to come into thermal equilibrium. Now, what you could do is not change the expansion rate. You could change the speed of light. Then it's easy to communicate over large distances and come to thermal equilibrium. It's been argued, can perform the same trick. Now, the BGV theorem assumes that the speed of light is the maximum, that there's 300,000 kilometers a second. That's as fast as you can go. In fact, that's the way the BGV theorem works. The way the actual theorem works is that you follow trajectories of what are called co-moving observers, and in a contracting universe, which you would have if you're going backwards in time, in an expanding universe, the speed of light goes up, 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 up. Well, it's got a limit, 300,000 kilometers a second. So that's how this theorem works. You get to this limit. Now, in variable speed of light theories, there's no limit to the speed of light. So I don't think that the theory would apply there. And in fact, there's a theory of quantum gravity, another rival to string theory, called Hodge-Lifshitz gravity. And that has the implication that the speed of light does indeed go to infinity in the quantum gravity regime. So I don't think anyone's shown that the BGV could apply in that universe, and I don't think that it could. But I think the most important thing is it's a classical theorem about a classical space-time. So who cares? Honestly, I mean, that is the attitude to many people. Like, the universe isn't classical. Who the hell cares what this theorem says? It just is irrelevant. So there are some people that say the theory is wrong. Some people think it's irrelevant, and some people think it can be avoided by a different space-time structure, like a collapsing universe. In fact, a collapsing universe is not the only structure you could imagine that would evade the BGV theorem. So there's many ways to evade it. One, different structures of space-time. Two, fiddle with some of the underlying assumptions, like whether the speed of light is really a limit, or three, go into some of the mass of the theorem and challenge that. So and there's even other ways that people have challenged it. I probably should stop there, but basically, the conclusion of a theorem that the universe has a beginning is shaky. Let's put it that way.
So, many things one might say in response there. And I have no axe to grind here, though I did grow up listening to William Lane Craig, admiring him, and I still think he's an excellent philosopher, but there are several limitations on his work that I now recognize, one of which may well be this one. But I guess I still hold out hope that the relevant science is the way that he's characterized it. So that is a bias of mine. But that being said, the first thing you mentioned was that the implications of the Borda-Guth-Vilenkin theorem can be avoided if we postulate a contracting phase. And that Craig responds, well, these models are problematic. Now, in fairness to Craig, and as you yourself said, Alexander Vilenkin makes these same criticisms. So it's not like cherry picking the scientific evidence. I mean, if someone as eminent as Vilenkin has criticized these models on those grounds, then I could understand why someone as a philosopher would say, okay, so this must be seriously problematic. But I think you're also right that there's always going to be developments at the leading edge of physics, science in general, that are going to question the assumptions of established science, but that doesn't mean that they're going to succeed. I think it's just natural that you're always going to try and question established results in the past. Most of the time, those results fail. So I don't know. I guess I don't know how significant I find it that there are currently models being debated on the edge of cosmology and physics that might end up reestablishing contracting models. There seems to be an initial low likelihood of success given the failure of the past. I don't know. I'm just trying to think through
Yeah, no, I can
ways
understand that. I
of.
mean, some people have said, people keep trying to establish eternal models
Hmm,
that are eternal in the past, and they keep failing. So this is an indication
yes.
that they will keep
Yes.
failing. To
Yes.
me, that's the wrong way to look at it, because the way I look at it is much more like a pendulum. So if you imagine a pendulum swinging back and forth, um, if you're on the left-hand side, you can always say, oh, it keeps moving away from me. But the same is true as if you're on the right-hand side, it keeps moving away from you too. So I think Craig had a phrase something like the history of cosmology is the graveyard of past eternal universe models. All right. Yeah. So I think that's something that he said. But you can just flip that around, right? You can make exactly the same argument for past finite models. You can say, hey, look, you had this early singularity theorem, and then it was shown that it relied on a perfectly smooth space-time. Well, that's ridiculous. That failed. Then along come Penrose and Hawking. Finally, they've established a beginning. Well, that also failed. And there are other reasons why Penrose Hawking is assumed not to be valid, other than the quantum gravity proposal that we talked about. In particular, one assumption of Penrose Hawking is that the universe is, well, let's put it simply, that the universe, gravity is always attractive in the universe. The technical term is an energy condition, but in plain language, it's the gravity is always attractive. Well, in 1998, hey, found out gravity wasn't always attractive. We found the universe accelerating expansion, and that's a repulsive gravity term in there. So turns out that one failed. The Penrose Hawking failed too. Then along comes Borda-Guth and Vilenkin. That says, oh, we don't really care about the energy condition. And that actually really the kind of the point of the theorem, that it's supposed to be insensitive to the energy condition. Um, but hey, if the universe was contracting in the past, then it's out. And along, almost immediately as Borda-Guth-Vilenkin is proposed, a whole bunch of quantum gravity models come out that show the universe was contracting in the past. Now, I don't want to say those models are correct. They are speculative physics. But I think anything about the early universe is speculative. So at the statement that there couldn't be a contracting, I mean, it's basically open. That's what I want to say. it's an open question. What happened, in these very early moments of the expansion? Was it a turnaround from contraction, or was it something else? There are other possibilities too. And many of those other possibilities can also avoid the beginning. Um, so now the fact that Vilenkin has sort of pointed out problems with collapsing universe models, to me, it is cherry picking. I'm going to be a little bit less charitable to Craig here, because there are plenty of people that propose, bouncing universes or cyclic. So there's two ways well, there's actually a couple of ways more than two actually. There's a few ways you can think about a collapsing universe. So one is that, straightforwardly, if we go backwards in time, if we live in an expanding universe, it's contracting if we run the clock backwards, and then if we keep going, it will just expand again, right? So that's one way you can think of it. So you'd have like an hourglass universe. So just think of a sort of mirror image, right? So two regions joined by a little bridge. So that's one way you can think of it. Another way you can think of it is what's called a Janus universe, where you have a reversal of the arrow of time at the middle point. Now, there's some debate. Craig likes to say that's then a beginning, because then time is pointing this way and then this way. So basically, in a conventional bounce model, the people in the contracting universe would see their universe contracting. But in a Janus universe model, the people in the other branch, they see their universe as expanding, because their arrow of time changes. So there's some debate about whether that model has a beginning or not. Craig likes to say it is. A lot of cosmologists say no, that's not a beginning at all. People disagree about that. A third possibility is you have a cyclic universe. So it maybe expands and contracts. Or there's other cyclic universes that don't even have expansion and contraction. There are other ways for the universe to be cyclic. And so now Vilenkin is a strong proponent of the universe having a beginning. And I think it's cherry picking, because there are plenty of cosmologists who have a different view. So to continually quote the same guy, known to be an advocate of a beginning universe, and then sort of discounting the views of other equally eminent cosmologists who have different views, that, I mean, to me, that is the very definition of cherry picking.
Okay, so it's cherry picking, but at a different level.
Right.
Yeah, I mean, maybe it is. I think you might be onto something there, but
Yeah.
I hasten to hedge my bets only because I don't know the field of cosmology nearly as well as I want to, or as well as you.
Well,
So maybe there's a way.
I hope that's where the book will come in, because what we do in the
Yes,
book is dive into these models in,
yes.
I wouldn't say in great detail, because we're still trying to make it accessible to a lay audience. So not in great detail, but more detail than what you'll get in a 1 hour YouTube video, or what you'll get, in a apologetics debate. Um, and also we tell the stories of the controversy itself. So what I did, I went and interviewed like everyone involved in this fight, as it were, and they all, sort of sling mud at each other. Um, so it's not always constructive. These are hot debates, and they get really quite lively. So to pick one side in the debate and just quote them, that's just dodgy. But what we do in the book is talk to both sides, and then you can be better informed when you read it, I hope.
Well, that's excellent. So there are a few points I want to take a closer look at. The first and perhaps most important is going to be this critique that you have made, that Dan has made, Dan Linford, that there's a methodological flaw, a fundamental flaw in the way that Craig argues for a beginning of the universe. And if it's cogent, it shows that his entire approach, wholly apart from his specific critiques of various models, is wrong. And that's that he seems to be arguing that here are models 1 through 10 that try to show how the universe could be eternal. They all probably fail because they each have these problems in them. And therefore, it's likely the universe had a beginning. And then the problem you point out is that you could reverse that argument. You could turn it on its head and say, here are 10 different models that show or feature the universe as having a beginning, but here are several reasons that each of these models are problematic, and therefore the universe is probably eternal. So let me read you Craig's response, and then we'll recap what you've said and go from there. Because I think there are some deep issues here about inductive reasoning that I don't think we've yet clarified. Because there are cases where, well, anyway, I'll read you his response and we'll go from there. Craig writes that the question is, which classes of models are physically tenable? Models featuring an infinite past are physically untenable. They cannot be right. By contrast, models with a beginning are at least physically tenable, such as the Vilenkin's model or the Hartle-Hawking model. And so he gives two illustrations of this idea of where you can rule out certain answers without knowing which one is correct. And the first would be like the evidence available at a crime scene. Well, that evidence, supplemented with other evidence as well, may well rule out the claim that my mother committed the murder. That seems right. Or that any of my relatives committed the murder. We live in an entirely different country, for instance. But we still have no idea who did commit the murder. We've just ruled out a class of potential suspects without thereby committing ourselves to any claim about which particular person remaining committed the murder. All right, fair enough. And then the second example he gives is that the evidence rules out Newtonian mechanics being the correct and final theory of everything. Newtonian mechanics is incomplete. We know this, but we don't know which theory, for instance, of quantum gravity is correct. So I think Craig has a point that it is not necessarily invalid to reason from the conclusion that certain sets of solutions are wrong, and therefore the right answer has to be among what remains, even if we don't know which specific solution it is. And what's not clear to me is whether or not Craig's reasoning is an example of that kind of reasoning, or whether it's an illicit type of reasoning akin to the one that you've illustrated, where you can just parody and reverse the arguments. And I think things get complicated. So why is Craig's reasoning not an example or akin to those two examples that he gives?
Yeah, okay. So I think let's go back to the crime analogy, the murder in the house. So let's suppose your method of ruling out, was it grandma or something? Or who would do
Or my
ruling out?
family members. I'm
Your
paraphrasing his example, but
okay,
yeah.
yeah, all right. All right. So we've got let's say 10 suspects, okay? And what we do, let's just say they're even or odd numbered suspects, okay? So we go to we number each suspect 1 through 10, and we look at all the even numbered suspects. And the way we're going to rule them out is to say, have they got an alibi? So we interview all the even numbered suspects, and they've all got alibis. And then we go, okay, it can't be any of the even numbered suspects, go home, right? Then we look at the odd numbered suspects, but we don't ask them if they have alibis, right? We just say, well, it must be one of you guys. That is not a valid way of doing an investigation, because you didn't do the same thing to one set of suspects that you did to the other set of suspects. So what he does is he goes through the universe models that he thinks are potentially past eternal, and he ignores, actually there are plenty of models that he doesn't touch, he doesn't even mention, but he does do a fair few, right? And he basically doesn't do any probing as to, I mean, as far as I know, the only models that he's ever proposed as having a beginning, that he's ever mentioned, are the Hartle-Hawking model and the tunneling from nothing model. So the Hartle-Hawking model, I can point you to a dozen different criticisms of it, you know, and I could do exactly the same that he does for the models that he doesn't like, and to just do exactly the same for the two that he has proposed that potentially have a beginning. And even the Hartle-Hawking model is even debated whether it even has a beginning. It's not even clear that it has a beginning. And there's another problem, that whether Craig can appeal to it, because it uses imaginary time, and he said imaginary time is physically unintelligible. So now this is something of an ad hominem against Craig, but it's a valid ad hominem. People should understand that there's valid and invalid ad hominems. So an invalid ad hominem is you're stupid, so the thing that you argue for must be wrong, right? Or you're ugly, so the thing you argue for must be. So that's an invalid ad hominem. That's a logical fallacy. But a valid ad hominem is to say you've got a set of inconsistent beliefs, so you better give up one of those beliefs, or tell me why I'm wrong to say that they're inconsistent. And so here what we're saying is there's an inconsistency in his approach, and it's fundamental to his approach to philosophy of time, as far as I'm aware, because he doesn't really want to allow imaginary time as a real physical thing. But that's how the Hartle-Hawking model works. So if you don't allow imaginary time into your ontology, it's not clear to me at all that you could even have that as a theory for the beginning. Um, and there are problems with the Vilenkin tunneling from nothing model as well. I mean, this is a model. I should explain what this model is. And of course, Craig has been extremely critical of this model. I should also add, even though he mentions it as an example of a model with a beginning, he's also been very critical of it because this is a model from nothing, like literally nothing. We're not talking a model from a vacuum fluctuation. Is not that. This is a model where the space-time itself fluctuates into existence from a state where there was no space-time. So effectively, the radius of the universe is zero. So now you could say, how do you have tunneling from a state with no space-time? That's a criticism that people have suggested. Another criticism that people have suggested, both of Hartle-Hawking and tunneling from nothing, is that these models are unstable, that they don't give you the smooth universe. So Neil Torok, who was a very prominent cosmologist, has criticized the Hartle-Hawking and the tunneling from nothing model as leading to a completely unstable vacuum, which would not be our universe. And as far as I know, Craig's never mentioned these criticisms. So we can just do exactly the same. We can mirror what he does with. Now, this is, of course, with his scientific approach to the beginning. Maybe he might say, well, I've got my philosophical arguments for a beginning, and that rules out a past eternal universe. So they just can't be right. That would be a different argument, of course, and we'd have to go down. Yeah. So that would veer us off into the pure philosophy world. But in terms of the science, what he does is he tries to find criticisms of models and then says, well, these are problems with these models, so we can eliminate them. Therefore, what's left is the beginning ones. But we could just do exactly the same. Here's a bunch of problems with beginning models, so we can eliminate them. And it's basically like what I said at the beginning. We eliminate the suspects who have got alibis and then ignore that we didn't even ask whether the other ones remaining, all the odd ones have alibis. And that's, I think, what he's doing. So it's just a completely invalid methodology.
I think that in Craig's mind, what he's accomplished, or what cosmologists have accomplished that he's reporting, is that these models have been refuted rather than just shown problematic. So, for instance, he might say, well, no, the right analogy here is that you've shown that the 5 individuals that you initially numbered off, say from pictures, they're actually dead. And so we know that it has to be the 5 that are remaining. So there have to be instances where the evidence against certain solutions is so strong that even if we haven't considered the problems or lack thereof of alternatives, we know that it can't belong to those class that features those problems. That might be wrong. It might be that in every single case, it's still always comparative, however vague. That we do have an implicit comparison in the background, like we know these other 5 are alive. It's just that when I think, for instance, about the Borda-Guthrie-Lincoln theorem, those if we agree the theorem is valid, let's just grant that it's mathematically valid. It does, the conditional is correct that if the universe is on average in a state of expansion according to a model, it cannot be past eternal. Then those models that meet that condition but have an eternal past, they have some sort of internal contradiction, and so they can't possibly be right. Their probability is 0, and so we can rule them out in that respect. And I wonder if what Craig could say is that as the theorems become more and more general, that is to say, have less and less conditions attached to them, they rule out wider and wider classes of eternal universes by showing this contradiction, if you will. And that gives some inductive grounds for generalizing from our observed sample space of models and saying, well, it's likely then that all such models will have a similar contradiction and thereby be ruled out. Whether or not we can say that there is a universe with a beginning, there hasn't been a similar theorem showing that universes meeting such and such condition and having a beginning aren't possible. Maybe I'm thinking out loud here,
Yeah,
but
no,
I'm
I
just
take
trying to
that. I mean,
play
you could,
Craig's advocate.
yeah, you could try and make an inductive argument that, we're ruling out a wider and wider class of models. So that he could try and do that, but and he could also try and say that yes, there's a logical contradiction in some of these models. But I don't think he's ever alleged there's a logical contradiction in having a past contracting universe, let's say. I want to make clear that past contracting universe is not the only option, but I'm just using that because it's a simple one to explain. There are other options. But so let's just stick with that one just because it's really simple to visualize. As far as I know, he's never made the allegation that that would lead to a logical contradiction. I mean, you could try and invoke the a priori philosophical argument against the past eternal universe, and that has its own problems, which we can unpack. But that's a really separate issue from cosmology. But if he doesn't do that, I've never heard him say there's a natural contradiction. What he has made, what he does do is sort of try and find particular problems. So, I mean, we can go into like one or two, but a lot of the time it's just wrong. So I'll give you an example. So one model that is very clear that has a past, well, I should say very clear. It's mostly agreed upon by researchers in the field. Nothing is perfectly clear in this world. But the consensus view is that, for example, in loop quantum gravity, which is a rival to string theory, it's probably the most well-known rival to string theory. In their cosmology, they have an hourglass universe. So it contracts. So basically, it contracts and then expands, and whichever way you look, that's what you're going to see. So if you wind the clock backwards, you'll find our universe is contracting, and then you'll get to the Big Bang. And if you keep going, you'll find it's expanding again. So his criticism of that was that dark energy has ruled this out. The discovery that the universe is accelerating in expansion has ruled out this activity because you couldn't have a cyclic universe if the universe is accelerating in its expansion. It's not going to recollapse. In order for it to recollapse, you don't want dark energy to exist or to have a positive value. So that's wrong on like multiple grounds. The first is that we don't know if dark energy is actually a cosmological constant. It could be changing over time. And if it changes over time, then actually the universe could recollapse. So dark energy doesn't rule out a recollapse in the universe. And in fact, we've revealed new results from the dark energy spectrographic instrument, which is the most accurate sort of way to look at dark energy. And their tentative results so far is that dark energy is weakening over time. So Craig would just be wrong about that if those results hold up. I mean, problem is you never know because all you can do is measure it to higher and higher accuracy, but you can never know for sure. So it's wrong on that level, but it's even worse than that because let's assume that dark energy is a cosmological constant and the universe will never recollapse. What does that say about whether the universe did recollapse in the past? Absolutely nothing, because all it's going to tell you, all the quantum gravity theory says is that if you get to that high energy density state, then you'll get a bounce rather than a singularity. That's what loop quantum cosmology says. So we go back in time, we know we're expanding now, and we find there's a bounce. Does dark energy change that? Not at all. You would then just have an hourglass universe rather than a cyclic universe. But since loop quantum gravity wasn't predicting a cyclic universe, it doesn't really matter whether we're going to have one or not. It's just totally irrelevant. It's like saying, well, I'm not going to be a child in my future, therefore I wasn't a child in my past. Well, that doesn't follow. So his way of ruling this model out is just totally. This is what's in the Blackwell Companion, and I'm just amazed that they publish this because it's just so obviously wrong. So that was, but that was the method that he used to try and rule it out. It wasn't appealing to a logical contradiction, and it was appealing to what he thought was a flaw in the model. And one, it isn't a flaw, and two, but of course the model could be wrong. There's no question. In our book, we have more than 20 different models for the early universe. Some of them get more airtime than others. But of course, so the chances that any one of them is right is pretty low. But it doesn't follow that the chances that any of them are right are pretty low. So yeah. So it's a bit like I think Dan gave the example of a lottery. I think actually it should be a raffle rather than a lottery. The chances of in a raffle that you pick out a winning ticket are low, but the chances that one of the tickets being picked out wins is guaranteed. That's how a raffle works, you know. So yeah, so what if one model is low probability? They're all going to be low probability. It doesn't matter.
Yeah, fair enough. I'm gonna have to just admit you've got the better end of the argument today. I can
Thank you.
I can
That's
freely admit
okay. You
it.
can come back. You can come back with something
Right.
better, I'm sure.
I'm gonna live to fight another day. I'm gonna do my
Yeah.
reading, get the case together, and then refute you one day. I just
Go for it.
I think here's my the reason that I'm playing Craig's advocate
No,
is that
yeah.
Craig is other, and this doesn't mean he's correct here. It's just it explains where I'm coming from. Is that Craig is otherwise an excellent philosopher. There are errors, I believe, in certain positions he's adopted. I disagree with him on a range of questions and issues, but he always has impeccable abilities as a philosopher, and his argumentation is widely regarded as very good within his field of philosophy, anyway. And often these issues are going to be interdisciplinary by nature. So even when scientists are talking about certain topics that we might ascribe to science, really it's an overlap between science and philosophy. So everyone is going to be to a degree outside their area of expertise. And so I look at someone like Craig and his otherwise strong, thorough, careful research and methodology. And I say, when we turn to something like the empirical evidence for the beginning of the universe, and someone comes along with a case showing that his argument is so obviously flawed that anyone could have figured it out by just thinking about it for 10 minutes, I find that inherently unlikely. Now, if you don't like Craig, if you have a different conception of who he is as a philosopher, different ideas about him, then that's not going to mean anything to you. But if you're approaching it from the place that I am, it does make sense to step back and go, maybe I and us are misunderstanding something. But that is where I'm coming from. I mean, I don't know. I don't know how thoroughly you're acquainted with his work. Would you agree that in certain other areas, he's an excellent scholar?
Well, I let me say some positive things about Bill Craig. One, I think he's incredibly smart. I think he's very knowledgeable. Like he talks about findings in a whole bunch of different areas of philosophy and science. So I think he's very smart, and I think he's the best debater on the theist side on the planet. He is amazing at doing debates. He is really, really good. And I think he's won most of the debates or tied that he's been in. And I can only think of two debates that he's done where I think he's clearly lost. And one, this is my opinion, one was with Sean Carroll and the other one was Shelley Kagan, sorry.
There we go. I was like, something's
Yeah,
wrong.
yeah, something's wrong there. um, those I think he did not do well, but in the others, I mean, that's a good track record. If you've done that many debates and you've only had two knockouts against you, that's damn good. You should be very proud of that track record. Um, Nevertheless, I think when it comes to representing science, this isn't the only beef I've had with Craig. So you probably know about my stuff on animal suffering, and yet again, I feel that he totally misrepresented the science. So here's what I see is that when it comes to representing science, I don't think he does it accurately. Now, I don't want to accuse him of lying. Um, I don't want to read his psychology. I can't do that. All I can say is that not only has he misrepresented the science, but when it's been pointed out that he's misrepresented the science, he hasn't said, yeah, okay, my bad, I made a mistake. Let's just own up on that one and say, yeah, I got that wrong. I've never seen him do that, not once, not ever. And I think, you know, he made go on the animal suffering thing for a slight moment. He made this claim that animals are not aware of their suffering because they don't have a prefrontal cortex. And we published a paper that I think absolutely obliterated that argument. And I've never seen him say, "Yeah, okay, I got that wrong." He's made the same argument as far as I know since then. Um, so I think there's an onus on him to either say why we got it wrong. I Phil's talking rubbish when he said he obliterated my argument. Here's why. I think there's some onus on him to do that, particularly on a topic that is really important. Whether animals experience morally significant pain is a damn important topic. It's not a minor little thing. It's huge. Like that has huge implications. Um, so so I'm seeing things a little more negatively than you, I guess. But I do want to acknowledge those positive things. He is super smart. He is really well. He's incredibly knowledgeable, and his skills as a debater are second to none. But that doesn't mean there isn't motivated reasoning going on. I mean, I guess we all have that to some extent. So I don't want to sort of isolate Craig and say motivated reasoning, but not us. But ultimately, I think we can't appeal to Craig's abilities in this field, particularly because he isn't an expert in this field. Um, Now, neither am I, but I do interview the people who are, and they tell me that he's wrong. So I think I have to go with them. And what I've tried to do is interview lots and lots of people with all the people that work on the Big Bang, and ask them, what do they think about these topics? I've just very recently, this is as recent as it gets. This very recent YouTube or podcast that he put out, responding to Dan and I's appearance on the Joe Schmidt podcast. Sorry, on the Majesty of Reason show, Joe's show. He quoted a paper as trying to sort of rebut the idea that there could be a past eternal universe. The author of one of the authors of that paper is someone I know. He's actually in a video that I've just released today. And I emailed him quickly and said, "Do you think you can rule out any of the possibilities that you explore to evade sort of past singularities?" He said, "No, I don't think we can rule any of them out." And that was the very scientist that he quoted. Um, so I just don't think that he is. He is. Look, I'm going to put it straight. I'm going to say it as straight as I can. He is misrepresenting the science on this particular topic. He may get other stuff completely right, but on this topic, and not the only, and also the animal suffering one, I think he's misrepresenting the science very severely.
So let's consider, if you have time,
Yep.
one more aspect of his recent case for beginning of the universe,
Okay.
which appeals to more cutting edge science.
Hmm.
And this would be Aaron Wall's generalized second law of thermodynamics.
Yep.
Is this something you're familiar with and have
Yeah.
thought about?
Yep.
Okay.
Yep.
So if briefly you can tell us, what is that generalized second law? Because Craig quotes it to the effect that it is a new singularity theorem of even wider applicability than the BGV theorem. And it shows that almost
Right.
any physically tenable model will feature a beginning of the universe and can even be extended into hypothetical quantum gravity models.
Right. So let's say first of all, we should say what the second law is. The second law is this law of entropy. It says entropy overwhelmingly is likely to increase into the future. Now, it's a statistical law, the second law. It's a bit, one analogy I think Leonard Susskind had with it was, imagine you have a table covered with coins, and they're all heads up. They've all got facing heads. Then you start flipping them. It's overwhelmingly unlikely to stay all heads. It's much more likely you're going to get a random mess of heads and tails. That is the overwhelmingly likely thing that will happen in the future. And that's really what the second law says. The second law says that entropy is overwhelmingly more likely to increase over time because there's more ways for the universe to be high entropy than low entropy. So then we could ask, what's the argument from the second law? The argument from the second law is that the entropy must reach a maximum value in some finite time. It's because eventually we'll just be in sort of thermal equilibrium. There's no usable energy. So there must be a past finite time, because otherwise we would already be in thermal equilibrium in this maximal entropy state. So that's the standard argument from the second law. The generalized second law, as I understand it, is that it basically includes black hole entropy. So um, there's this whole issue of entropy of black holes, and maybe we can do quantum gravity by looking at the entropy of black holes. It's a whole long rabbit hole that we don't have time to go into. So what Aaron Wall published a paper saying generalized second law implies a quantum singularity theorem. So there's a couple of issues here. One is that it's the same. Well, I mean, I'll tell you what the experts I've spoken to about this say. So one was the Bayash Takar, who is also a leading expert in this field. He was the founder of loop quantum gravity. He's the winner of the Einstein Prize, which is the highest physics prize you can get from the American Physical Society. He's the president of International Society for General Relativity. So he's equally esteemed physicist as Aaron Wall or Alex Valenkin. In fact, he's the editor of the journal that Wall published his paper in. Um, and he basically said, I asked him about this, and he said, well, the problem is he's assuming that thermodynamics is fundamental rather than emergent. So he doesn't think that this would be a fundamental feature of a quantum gravity theory. And in the paper, what that Wall said was that this may apply to quantum gravity, but it doesn't follow that it does, right? People just don't agree about that. Also, he's basing it off something called the Penrose theorem, which was like the earlier version that Penrose Hawking worked on, but it was Penrose by himself. This sort of assumes that space is infinite. Now, Craig's, again, this is an ad hominem against Craig, but it's a valid ad hominem because he thinks that infinities are impossible. Therefore, he cannot use the Wall theorem. Maybe someone else could, but he can't. So, he should tell us which one of these things he has to give up. Now, then he said, well, we put this in the video, and he said, well, you know what? If you take off the infinity assumption, then the generalized second law just reduces to the ordinary second law. And then you get this argument. So then we could ask, what's wrong with this argument? Why don't we think that this is a valid argument going from the second law to the beginning of the universe? There's a number of problems with it. One, pointed out by Alan Guth, was that we don't know what the maximal entropy of the universe is. If it could be infinite, in which case, you can go forever. If the maximal entropy of the universe is infinite, then it's not clear that you have this problem. Also, in eternal inflation, it's not clear that you can even define what the maximal entropy even is. Another problem is that some people have alleged that entropy is actually an observer-dependent effect. So remember the example I said of the coins on the table. This was the example given by Leonard Susskind, another very, very prominent theoretical physicist. Now, note that how did he determine that the random distribution of heads and tails was high entropy? Well, because there's more ways for it to be heads and tails than it is to be just heads, all right? But some people have argued that, well, but think of it another way. That whatever distribution you got, let's suppose there were, I don't know, 100 coins on the table and you had 50 heads, 50 tails, okay? That's supposed to be high entropy rather than all heads is supposed to be low entropy, because there's more ways for there to be less ways for there to be all heads than there is to be half heads and half tails. But you could argue that, well, if you just positioned all the heads, you said, right, in this position heads, this position tails, you said, well, actually, that's equally as unlikely as all heads. And so what you consider to be low entropy is not necessarily what I consider to be low entropy. So it's actually observer dependent. So what Carlo Rovelli argues is that it's a bit like the sun moving. It doesn't really set. It just looks like it sets. So similarly, the universe actually wasn't low entropy in its earliest form. It just looked like it was to us. Another problem pointed out by the I forget the name of the philosopher that pointed this out. Oh, damn it, I forgot. All right, a philosopher pointed this out, was that there's a problem, which is that a low entropy state is improbable anywhere on the timeline of any universe. So now let's imagine. So what we could imagine, imagine we. So actually, let's pass that for a sec. Another option that you could have is that let's imagine you've got this contracting universe, then it expands out. How do you solve this low entropy problem? Well, it could be that the entropy of the previous universe is just sort of trapped there, that it doesn't go through. So we sort of wipe the slate clean. And that there could be mechanisms that allow that in quantum gravity. There's been proposals for that. Well, let's just suppose we thought it was what Susskind might suggest, that it was just super random lucky that it got to zero entropy at the middle of this hourglass universe. Seems extremely unlikely, right? Nobody could take that seriously. It's so unimaginably unlikely. But you could argue that the low entropy condition that we see at the Big Bang, is unlikely on any model. Like, let's imagine it's the beginning of the universe. We put the beginning there. Why did it start with a low entropy state? That's equally as unlikely there as it would be in the middle. So it's equally unlikely at the beginning of a beginning model as it is in the middle of an endless model. So this entropy argument doesn't favor one model over another. So that's how we can sort of think about this entropy argument. Does that make sense?
I wonder, though, are you running together two different arguments that theistic philosophers had made surrounding entropy? On the one hand, there's this uh, entropic argument for a beginning of the universe, because if the universe has been around for infinite time and entropy always increases, and there is a maximal point of a ceiling to how high entropy can go, then we should already be at that state. But then there's an independent argument concerning the fine tuning of the initial condition of low entropy that we apparently observe in our universe. And I wonder if you're not clearly distinguishing those two, because questions about the probability or improbability of a low entropy condition, it seems to me, don't have a bearing on this
Well, I
argument
think they
for
do. No,
beginning
but
of
I
the
think they
universe.
do. I think they're related, and the reason
Okay.
that they're related is that the argument is that we would be in this maximal entropy state if the universe was eternal. Okay, but let's just suppose I said, well, let's just suppose halfway through this hourglass universe. So we're imagining this hourglass universe now. So we have a Big Bang, expands to infinity, and there was a collapse from infinity in the other branch. Okay. So the question would be, how could it be that we're not already at infinite entropy? That's the question. That's the argument. We would be at infinite entropy. Well, let's suppose I put in, well, halfway through it just randomly went to zero entropy. It's possible, right? Because the whole point of the second law is it's a probabilistic law. It says it's incredibly unlikely that you throw all these coins and they all come up heads. It's much more likely that there'll be a random mess of heads and tails, right? That's how this argument is going to work, right? So if I said, well, no, we just got really lucky. When it went through the bounce, the entropy went down to zero. The counter argument is going to be, well, that's unimaginably unlikely, so that's not going to work. But I could just say, well, it's unimaginably unlikely for a beginning universe to have this incredibly low entropy start as well. So that's why I'm saying it doesn't favor one model over another one, because they're both equally unlikely. And I think what Penrose has made this argument that about this fine tuning of the entropy, and he's got this number 10 to the 10 to the 120 or whatever it is. But it's very important to know that that's often misquoted in the fine tuning argument, right? Because what he's not saying is that number is fine tuned for life. It absolutely isn't that, because the entropy could be enormously higher and life would still be here. What he's saying is, if you randomly selected universes that you had to live in, right, you don't need the entropy to be that low. So why is it so low? And I think a better answer is that there was and this is the answer Penrose himself favors, which is often left out when the people quote Penrose in these fine-tuning arguments, is that there was a universe before the Big Bang. And if there was a universe before the Big Bang, as you transition from the pre-Big Bang universe to the post-Big Bang universe, there is some mechanism that resets the entropy to zero. That will do the trick, and that will let you live in an infinitely old universe. So that's what he suggests. Now, other people have different mechanisms for this. So if you talk to some quantum gravity people, they will not say the same thing as what Penrose says. You know, as to how this thing could be reset, if you like. But the bottom line is the argument does relate to the probabilities in my opinion.
Okay, fair enough. That seems right. But then, of course, if your resolution to the problem of non-maximal entropy to avoid a beginning of the universe is to say that really we just inhabit a local fluctuation from a much wider state that is in maximal entropy, either over time or at one point, but in space, then you immediately land with the Boltzmann brain problem. That if we say that our state of low entropy was a fluctuation, a random fluctuation from a sea of maximal entropy, and that's why we observe a non maximal state, it's overwhelmingly more likely that a single brain would fluctuate into existence and have chaotic observations or completely illusory experiences than that an entire universe of low entropy would fluctuate in that way. And so, on the probabilities alone, each of us should conclude, given this explanatory mechanism, that we are an isolated Boltzmann brain, which raises all sorts of problems and is usually taken as a negative implication of one's models. And I know that that's an open conversation and it's a can of worms, but that would then be where the dialectic would go, I'd imagine.
Yeah, no, I think that's right. But I don't think anyone's seriously considering that the universe was just a random fluctuation. When I said, well, we just got lucky, the bounce, and it went to zero entropy, I was only just using that as a sort of parody argument, as saying that if you had that in that model, it's no worse than having it at the beginning of a beginning model, right? I could just make the argument. The same argument basically. So I wasn't. No one's seriously thinking that the universe was just a random fluctuation from a high entropy state to a low entropy state. That the arguments that people have are not that, but rather they're things like there was some mechanism that effectively that you don't get in the normal evolution of the universe, but you do get as you cross over from the pre-Big Bang universe to the post-Big Bang universe that sort of sets the entropy to zero, if you like. So that's unique to that. There are other ideas as well. How maybe you could have a different version of this. So Sean Carroll, for example, has a model where baby universes bud off from a mother universe. So so if you think about it, even in a universe that's massively increasing in its entropy, there can still be regions of low entropy, right? That's easy, right? And if they bud off and birth new universes, they will have low entropy. So we see this low entropy beginning, but what we don't see is the sort of mother universe that's just always increasing in entropy. So you can have this eternal universe in that sort of structure. This is the famous Carroll Chen model. Another possibility that we talk about in the book is the what's called de Sitter equilibrium model. So here, what would fluctuate into existence is not a new universe as such, not a fully formed universe, with like stars and galaxies. Because yeah, you're right. I mean, it seems more likely just a brain would fluctuate than you know stars and galaxies and structures like that. But think back to inflation. Inflation was this exponential. We can do a little call back to our beginning of our conversation as we end things now. Yeah. So that was the theory that said that the universe evolved from this unimaginably tiny seed, and that tiny seed is all you need to get the universe going. And it could be subatomic speck in size, and all you need is this tiny seed of inflating space, and that's enough to generate everything that we see in the universe. Now, what Andy Albrecht, who was one of the other founders of inflation, he didn't get the Dirac Prize because he was he was Paul Steinhardt's PhD student when they were working on this. So, but we'll open a tribute to Steinhardt and Albrecht on one side, and then Andre Linde on the other. This solution, remember that we had this graceful exit problem in inflation. So, what he suggested is that you have this model where what would fluctuate into existence is not universes fully formed or anything like that, but rather just one of these inflationary seeds. And it seems much more likely that an inflationary seed would fluctuate into existence than a brain. Brain is the most complicated object that we know exists in the universe. It has tens of billions of neurons. It has I don't know, 1 trillion connections, something like that. It's the most complicated object that we know. So what's more likely to fluctuate into existence, one of those or a little inflationary seed? Well, maybe the little inflationary seed is more likely, in which case you can actually have this sort of fluctuation. So he kind of turns eternal inflation on its head, um, and says, well, in eternal inflation, what you have is all these bubble universes, with one of them, being ours. But so you basically say it's mostly in inflation, with sort of rare deviations out of inflation. But you could go the other way, and you could say, well, it's mostly not inflation, but with rare deviations to inflation. Um, and that could be another way out of the Boltzmann brain problem. But the bigger issue with the Boltzmann brain problem, even more so, is that there might be an infinite number of brains, but there would be an infinite number of normal galaxies too. So now, how do you know which is more likely when they're both infinite? That depends on what's called a measure. So a measure is a way of doing probabilities, if you like, in infinity. So the analogy that we have in the book is to think of a deck of cards. So if you think of what's the chances of getting an ace in a deck of cards? It's like 4 out of 52. Yeah, there's 4 aces, there's 52 cards, right? If you have 2 decks of cards, the probabilities don't change. The probability is exactly the same, right? Now, what if you have an infinite number of cards in this deck? What are the probabilities then? Well, if the deck is ordered in exactly the same way, the probabilities stay exactly the same. They do not change. It doesn't matter if you have a 52 cards or infinite number of cards. But you can order them differently, and then you get different probabilities. So the normal way you order a deck of cards is like ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, picture cards, then ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, picture cards, and you have that 4 times in the deck, right? But what you could do is have 4 aces, then 4 other cards, just non-aces, right? Then you can have another 4 aces, and you just keep going. And now in this scenario, aces are more common than any other card. You might say, well, how can you do that? Well, you can't do that in a finite deck because you're going to run out of aces. But you're never going to run out of aces in an infinite deck. So the probabilities depend on the ordering. Now, now, how does this equate to the history of the universe? Well, it depends on what an average observer would see. That's the measure. That's the sort of equivalent of the ordering of the deck. And the problem is we don't know what the measure is. And so we can't necessarily say, when you have things that are infinite, which is more probable. It depends on a measure. And maybe you can fix the measure by some other principle. And physicists are looking for a measure that will do that, and hence can do probabilities in an infinite universe. But that's a difficult task, not yet done. So yeah, well, we probably should leave it there then.
Yeah, the measure problem is complicated, but I
Yeah,
suppose if one is taking a cumulative case approach to arguing for God's existence, and say they employ both the fine-tuning argument and the Kalam cosmological argument, they might be willing to grant you that the measure problem undercuts the Boltzmann brain objection to these ways of avoiding a beginning of the universe. But then they'll say that that same objection, the measure problem, will also undercut multiverse explanations of fine tuning. And so it's both.
Oh,
or
no, it
neither.
is. Yeah. Well, but no, I agree that the measure problem is a problem for the multiverse, because particularly if you want to empirically confirm there's a multiverse or inflation, if you like, then you do face a measure problem. I totally agree with that. But we can flip it around and say there's also a measure problem for the fine tuning problem, because we can say, well, how many values are there for the constants of nature?
Yeah.
All right. Oh, infinitely many. It could be anything. So now, what's the probability of getting the ones that we got? It's not so straightforward because you've got an infinite set. So there are lots of problems with the fine-tuning problem itself, suffering
Yes.
from a measure problem.
Well,
So
all
I
right. I mean,
agree that these measure problems are problems, but they're
yes.
problems for both sides, in my opinion, not for
Well,
one side.
And we can continue notching it forward, because that one is the
Yeah.
normalizability objection to the fine-tuning argument. And fine-tuning now gets more into my wheelhouse than the things I
Okay.
know of. I
Yeah,
think
yeah,
that problem is solvable, but I think we've canvassed enough material for this
right.
podcast. I think
Sure,
we should
sure.
discuss fine-tuning in the future.
Yeah.
I would like to, at some point, if you're willing, talk about fine-tuning specifically related to your documentary that you did, not
Okay,
on the
sure.
cosmological argument, but on fine-tuning, because I think it was very
Sure.
well done, and
Yeah,
it
thank
relates to
you.
things I know more about.
Okay,
And
sure.
yeah,
Yeah. Yeah, happy to. Yeah. Yeah.
excellent. Well, did you have anything else you wanted to say on these topics of God, the beginning of the universe, and William Lane Craig?
I would just say buy the book, Battle of the Big
Yeah.
Bang, coming out in May, because we're going to
Yes,
dive into all this. And I think it's a thrilling ride. And we've got fabulous reviews from people like Carla Ravelli, Roger Penrose, Sabine Hossenfelder, Stefan Alexander. I mean, the list is quite long now. So check it out. I hope you'll all enjoy it and find it fascinating.
I agree. I second the request. And I guess I'll end by saying thank you for coming on the podcast. This was a great conversation.
Yeah, it was a lot of fun. Thanks for having me on. Cheers, Ed.